So what I want to do in this video is to talk about section 11.4, and this is going to give us another test called the alternating series test. Before we get into that, I want to revisit some of the tests from earlier in this chapter. So namely, there's the test for divergence, which says that if you have a series, a sub n, and if the sequence of the terms, a sub n, the sequence that we're summing, if that sequence does not go to 0, then the series diverges. So just for example, if the sequence tends to 5, so if when n is large, if a sub n is about 5, then when you look at the series a sub n, you're adding up 5 infinitely many times that has no choice but to go to infinity. Okay, and so that's the divergence test in a nutshell. Unfortunately, if the sequence a sub n does go to 0, that tells us nothing. There's examples where the sequence tends to 0 and the series converges, and there's examples where it diverges. It just doesn't tell you anything. So if the sequence goes to 0, then we just have to do a little bit more work. On the other hand, if the sequence does not go to 0, then we know that the series diverges. That's the end of the story, and that's the divergence test. Okay, and so we learned that among other things in 11.2. In 11.3, we talked about the integral test. And the integral test basically says that series and integrals behave a lot alike, and namely, if you look at the sum of, say, 1 to n of a sub n, this converges if and only if the integral from 1 to infinity of f of x converges. Okay, where the connection between a sub n and f of x is that a sub n is f of n. So for example, we looked at 1 over n squared and 1 over x squared, okay, where that's kind of the connection there. So that's the integral test. And actually one of the things that we talked about in the integral test that I'm not sure I ever explicitly wrote down, but if you draw a picture, and I think this is worth just drawing one more time. So imagine that you have a function f that's positive and decreasing to 0. We know that, it's kind of unnecessary at this point, but we know that if the values are not going to 0, both the integral and the series will diverge. So suppose you have a function f that's decreasing to 0. And then let's draw a picture. Let's think about what the rectangles are. So this is the value at 1, this is the value at 2, 3, and so on. Okay, and so the integral is going to be the area under this curve. We know that that's the integral, of course. And then we can compare that to f of 1, which is going to be the height. We could think of it as a rectangle with width 1, and the height is f of 1. And likewise, f of 2, f of 3, f of 4, and so on. And then remember what we did, and I even wrote this. I think I even kind of wrote this down. But you can take all these areas and you can kind of slide them over so that they all fit in this box here, and they all fit inside this rectangle. And so this rectangle is at most this rectangle is of size f of 1. And so therefore, what we actually just showed, if you think about it, is that the series a sub n is greater than the integral because the rectangles stick above the curve. But it's less than or equal to f of 1 plus the integral from 1 to infinity. Because again, it's the area under the rectangle plus this extra bit here, which is f of 1, because it's the height f of 1 times width 1. Okay, and so this is actually a quantitative version of the integral test. So if one of these is finite, so is the other. And if one is infinite, so is the other. Okay, that's really the only way to make sense of these inequalities that I've drawn here for the integral test. Now, in 11.4, and that's really the content of this video, we're going to talk about what are called alternating series. Okay, so if we have alternating series, what's going to happen here is we're going to be looking at things like negative 1 to the n or negative 1 to the n plus 1 times some sequence. Okay, so let's say 1 over n or 1 over n squared or something like that. And so this is going to be, in this case, if n is 1, we get 1. If n is 2, we get minus a half. If n is 3, we get plus a third. Okay, and so on. And so the alternating refers to the plus minus pattern that you have, so the signs alternate each term, hence alternating series. It turns out, by the way, that this is called the alternating harmonic series, because if you didn't have this negative 1 to the n, you'd have the harmonic series, except this time it converges, and it happens to converge to the natural log of 2. Okay, and we'll say a lot more about this alternating harmonic series in later sections, so in 11.7, 11.8, and 11.9. Okay, we'll actually prove that this converges to the natural log of 2. We'll do a few other things as well. So that's alternating series in a nutshell. That's what an alternating series is. And then we're led to the alternating series test. Okay, so the alternating series test basically is a very nice, neat condition for when the alternating series converges. And so let's consider the series negative 1 to the n or negative 1 to the n plus 1. It actually doesn't matter. Starting at 0 or 1 or whatever you want. Okay, the first few terms are going to affect what the value of the series would be, but not the convergence or divergence. Right? If I were to take the so what I mean by that is that if I were to take the alternating harmonic series and throw away the first few terms, that would change what these values would be. This would converge to now negative, so natural log of 2 minus 1/2, whatever that is, if I got rid of the first two terms. But it would still converge, right? Throwing away the first few terms does not affect convergence or divergence. It just affects the value that it might converge to. Anyways, so if we have negative 1 to the n times b sub n, this is going to converge. So this converges if b sub n is a sequence that's greater than or equal to 0, and if it's decreasing, and if the sequence tends to 0. So if you have a positive decreasing sequence that tends to 0, then that corresponding alternating series converges. So, for example, our b sub n, if we look at the alternating harmonic series, by the way, I'm not going to write it, but I could have also written this with a plus 1 instead. Okay, so that again just tells you which sign goes first, if it's a plus 1 or a minus 1, but they're both called alternating series, as long as the signs alternate each term. So if I look at negative 1 to the n plus 1 times 1 over n, the sequence that we're looking at is b sub n, which is 1 over n. And 1 over n we know is a positive value. Okay, n is positive, so 1 over n is positive. It's decreasing, because it's like 1 over x, so the derivative is negative 1 over x squared, which is always negative. And it tends to 0. We know that the limit of 1 over n is 0 as n goes to infinity. And so this is exactly the type of thing that converges according to the alternating series test. And I think it's worth just saying a little bit about why the alternating series test works. In one direction is actually very easy. If these values do not tend to 0, so if the limit of b sub n is not 0, then the values negative 1 to the n times b sub n will also not converge to 0. Okay? The only way that this value can converge to 0 is if, when you take absolute values, that also converges to 0. And that's actually something that we talked about. Okay? A sequence will tend to 0 if and only if its absolute value tends to 0. We did that in 11.1. And the reason why I bring that up is that if this sequence, negative 1 to the n times b sub n, does not converge to 0, then the series diverges by the divergence test. Okay, because then we would have a series where the sequence doesn't tend to 0 and therefore diverges. End of story. We still have to tackle what happens when the sequence does converge to 0. And I want to talk about, basically with an example, I want to show you why this works when we have a positive decreasing sequence tending to 0. So let's look at the alternating harmonic series, and let's think about how this is going to work. So if we have, let's look at the series. So we're going to look at, this is going to be kind of the sequence of partial sums here. So I'm going to call this S of n and n here. So if n equals 1, this is going to take the value 1. And if n is equal to 2, this is going to be 1 minus 1/2, so that's 1/2. And if n is equal to 3, we're going to take 1 minus 1/2. So here s1 is 1, s2 is 1 minus 1/2. This is the sequence of partial sums. 1 minus 1/2 plus 1/3. 1 minus 1/2 plus 1/4 for s sub 4. Okay, so we're going to take 1 minus 1/2 plus 1/3. And then, so that's, let's see, 1/2 plus 1/3 is 5/6. And then minus 1/4. Okay, something like that. And then plus 1/5 minus 1/6. And so what ends up happening is that you can tell that these values are going to converge to this limit L. And the values that we happen to have converge to 0.693, something like that. So the natural log of 2. And so what happens, if you think about it, is that when you're alternating, you're going from above the value L. So here you're above the value, and then below, and above, below, above, below. And so the alternating part keeps you close to the value L. The fact that this is decreasing is also important, because that means that each time you get closer to L, and the fact that the sequence tends to 0 tells you that eventually the differences between the positive and the negative values are going to go to 0, and therefore you're going to settle along that value L. Okay, so that's how basically the alternating series test works. Okay, and so I'm not going to write up a formal proof of that, but this is the idea. Okay, so that's the alternating series test in a nutshell. Let's just do a few examples. So let's do a few examples. So if I look at negative 1 to the n times n plus 2 over n plus 5, as n goes from 1 to infinity. This is going to diverge. So this diverges since n plus 2 over n plus 5 does not tend to 0. Instead it tends to 1. So that tells you the original series diverges because the values don't tend to 0, and we're done. This alternating series test is actually very nice. N equals 0 to infinity, say negative 1 to the n times n over n squared plus 1. This will converge. So this converges since n over n squared plus 1 tends to 0 and is decreasing. You can check that it's decreasing by plugging in different values here. But since that value tends to 0, because it's decreasing, then everything's fine. Okay, so it's a positive sequence that tends to 0. I think actually if you go back and look at these, it doesn't actually even have to be decreasing. I think you can actually get rid of the value. The fact that it's decreasing, all you really need is that the sequence is non-negative and tends to 0, because the only thing that can happen there is that the values get smaller and smaller, and you know, the sequence of partial sums gets closer and closer to L. So I think having this be decreasing is actually even extra, and this will work otherwise. There will be a place where it's important that this is decreasing, and we'll talk about that later. Okay. But for now, if we just want to test convergence or divergence, we really need to look at that limit and just make sure that the terms are positive. The reason why the terms have to be positive is that, for example, you had negative 1 to the n times negative 1 to the n over n. Well, here this is again going to 0, because you could use the squeeze theorem. Negative 1 to the n over n is always between negative 1 over n and 1 over n, both of which tend to 0. But when you multiply these together, what's going to happen? You're going to get negative 1 to the 2n, and so what's going to end up happening there is you'll get 1. And this is going to be the harmonic series, which diverges. So it turns out that the alternating series test doesn't actually apply there, because it's not actually an alternating series. The negative 1 to the n times negative 1 to the n, that's it, so that each term is positive. So we need the b sub n, this part, to be greater than or equal to 0 and tending to 0. And then we'll get convergence or divergence. Okay, and that's really all I want to say in the video. I think alternating series is a really nice, easy to grasp idea with series, and we'll do some examples in class, of course, but this is the main idea.